Welcome back to Calculus Conundrums, the applications of derivatives by the perfect square. In this video, or actually I should say videos because it'll probably take more than one, we're going to talk about putting everything together that we've discussed so far in this session. So we're going to learn how to sketch curves, and we'll learn other characteristics about curves that involve us utilizing algebra and calculus. So you already know how to find x and y intercepts and identify symmetry. You know about domain and range and continuity. Most of this is algebra. Vertical asymptotes and horizontal asymptotes are probably, sort of a bridge between calculus and algebra. But then when you get into differentiability, extrema, concavity, and certain things like slant asymptotes, then we're talking calculus. So basically, we're going to identify as much of the above information as possible, and then we're going to use the information to sketch a graph without using technology. Now, on the pictures I'm going to use, you're actually going to see the graph's already laid, but you have to pretend like that the graph is not there. So I'll show you what I'm talking about when we get to the first example. Okay, so I'm going to start you out with a polynomial function. These are generally the easiest functions to analyze and gather the information from. So the function is 3x to the fifth minus 5x cubed. Now, over here I've kind of explained some things, and then over here I did some work. So the first thing I wanted to show you was that if I let x be 0, then the y value is going to be 0. So that tells me that the x-intercept is simply, or the y-intercept is actually the point 0, 0, which is also an x-intercept. Okay, now the other thing I'm going to do, since I let x be 0 there, I'm going to now let y be 0. And so if I let y be 0, I would be solving this equation, 3x to the fifth minus 5x cubed equals 0. And then I can factor out an x cubed out of that. And when I factor out an x cubed, I get this equation, x cubed times 3x squared minus 5 equals 0. And then that allows me to set x cubed equal to 0, or 3x squared minus 5 equal to 0. Now, the x cubed equal to 0, that just leads to this right here, x equals 0. But when you set this equal to 0, it leads to, if you add 5 to both sides, then divide by 3, you get x squared equals 5/3. So x would be plus or minus the square root of 5/3. Now, notice I gave you the exact value here, plus or minus square root of 5/3. And then over here, I go ahead and give you the approximations. That way we can kind of know where to put these intercepts when we get ready to graph. Now, the domain of all polynomial functions is all real numbers. So we know that. And it turns out the range of this function is also all real numbers. You probably wouldn't be able to tell that from the graph, from the original function. But when we look at the graph, you'll see that. And polynomials are continuous for all numbers within their domain. And I've already told you that we have 3 intercepts, one at 0, 0, one at square root of 5/3, 0, and one at minus square root of 5/3, 0. Okay, now since this is polynomial function, we have no asymptotes. So there's no asymptotes. Now, the next thing I'm going to do is I'm going to determine where the function is increasing, where it's decreasing, and if it has extrema. So if you remember, the way we do that is we take the first derivative. So here is the first derivative right here, 15x to the fourth minus 15x squared, and you can easily differentiate this original function up here to get 15x to the fourth minus 15x squared. And then after we do that, see if I can catch this little guy here. All right, now then we would set it equal to 0, and then we would factor out the common factor, which is 15x squared times, that would give us 15x squared times x squared minus 1. And then we would set x squared equal to 0, or x squared minus 1 equal to 0. And so then you can see that if you solve x squared equals 0, you get x equals 0. And if you solve plus or minus 1, if you solved x squared minus 1 equals 0, you get x equals plus or minus 1. So those are our three critical numbers. Now, what I did here is I went ahead and set up the table so we can determine when the derivative is positive and when it's negative. And right here, I couldn't put this infinity symbol, so I just wrote in INF for infinity. So minus infinity to negative 1 would be one interval. The next interval would be negative 1 to 0. The next interval is 0 to 1. And then the last interval is 1 to infinity. And then you take one of these numbers, a test number from each interval, and plug it back into the derivative. Now, when I plug negative 2 into the derivative, it's probably easier to plug it in here. If you plug negative 2 in, 15x squared is going to be positive, and then x squared minus 1 is going to be positive. So you have a positive times a positive, so the derivative would be positive. So the function is increasing on that interval. And then if you plug negative 1/2 in for this interval, you would get negative 1/2 squared times 15 would be positive. And then if you square negative 1/2 and subtract 1, you get a negative. So positive times negative would be negative. So there's a minus sign just showing you that the derivative would be negative. So the function would be decreasing. And it turns out it would also be decreasing for 0.5, for positive 1/2. So that was the number that I chose between 0 and 1. And so it's negative for that value too. So it's still decreasing from 0 to 1. And then if you plug 2 in, you'll find that the derivative is positive again. And so it's going to be increasing on those intervals. So basically, if you look over here, I know it's increasing on those two outermost intervals, negative infinity to negative 1, union 1 to infinity. And it's decreasing on the innermost two intervals. And since it didn't change here at 0, I can go ahead and say it's decreasing from negative 1 to positive 1. Okay. So we'll take a look at that a little bit later. Now, down here, if you're wondering what this is I applied the second derivative test. You might remember that I told you that if it's a polynomial, the second derivative test sometimes works better than the first derivative test. Now, I realize if I had to find out where it's increasing or decreasing, I already know the answer, because if you consider the first derivative test, the derivative is positive here and negative here, so at negative 1 we get a relative max, and then we don't get a change of sign at 0 as you cross 0, and then you get a change of sign as you cross 1 from negative to positive, so we get a relative min. So I actually could just use the first derivative test to determine that at negative 1 I get a relative maximum, and at positive 1 I get a relative minimum. And then of course I got the 2 by just plugging, and the negative 2 here, by just plugging the values into the original function. Now, but let me go, since I wrote the second derivative test, let me just show you what I did here. So remember, you get the second derivative, 60x cubed minus 30x, just going to be the derivative of this. And then if you evaluate the second derivative at each critical number. So if we evaluate it at negative 1, it's actually going to be a negative number. So that tells us that the function evaluated at negative 1, which is 2, is a relative max. And if you evaluate the second derivative at positive 1, you get a positive number. And so the function, at 1 is actually going to be a relative min. And at 1, the function equals negative 2. And then when I plugged in 0 for the second derivative, I got 0. So that told me the test fails. And then so I had to go back to the first derivative test, and you can see here the test does not yield an extrema here because the sign is the same on both sides of 0. So that just sort of confirms what I showed you, that I get a relative max at the point negative 1, 2, and a relative min at the point 1, negative 2. And then the next thing we would consider is the concavity. And since we already have the second derivative, then what I can do there is I can take that second derivative and set it equal to 0. and if you set that equal to 0, you'll get x equals 0 for one possible point of inflection. And then if you solve this equation, so you can take that over here somewhere and solve it. So if you get this equation, you would add 1 to both sides and then divide by 2. So you would get x squared equals a half. And then so x would equal plus or minus the square root of a half. And I went ahead and gave you the approximation for that so we'd know where it is on the graph. It's about 0.7. So actually it's, I should have said approximately plus or minus 0.7. So let me go ahead and put that. Okay, so that's really plus or minus 0.71, or we can just say plus or minus 0.7 when we get ready to graph it. Now, what you want to do is you want to do a table here, and so I'm going to set that up for you in just a minute. Okay, so look at my table here, and I actually, for the square root, I just used SQ, so I didn't have the symbols for that. So the first interval goes from minus infinity to minus the square root of a half. Then we go from minus square root of a half to 0. And then we go from 0 to positive square root of a half. And then we go to from square root of a half to infinity. And that's because I had these three numbers as possible points of inflection. Now, I need to evaluate the second derivative at test numbers. So I chose -1 in this interval, -0.5 in this interval, 0.5 in this interval, and 1 in this interval. Now I know square root of a half is about 0.7, so I know that from negative infinity to -0.7, -1 would be in there, and from -0.7 to 0, -0.5 would be in there, and so on. Alright, now plug this test point -1 into your second derivative, and it will be negative, so that means the graph is concave down on that interval. Plug -0.5 into the second derivative and you'll get a positive value, so the graph is concave up on that point, on that interval. And then plug 0.5 in and you get a negative, and so the graph is concave down on that interval. And then plug 1 in and you get a positive, so the graph is concave up on that interval. So look where the concavity changes. It changed from negative to positive when you cross this value, x equal negative square root of a half. And it changed from positive to negative when you crossed 0. And it changed from negative to positive when you crossed positive square root of a half. So each of these x value yields a point of inflection. But the point of inflection is actually the x and y value. Now, what you would have to do, and I'm not going to do that here, but what you would have to do to get these y values is you would actually have to go back to this function way up here, and you would need to plug in minus the square root of a half into this, then you plug 0 into this, and then you plug positive square root of a half into that and see what you get. Now I got, when I plugged minus square root of a half in there, I got 7 over 4 square root of 2. And then when I plugged 0 in, I just got 0 for the y value. And when I plugged square root of a half in, I got -7 over 4 square root of 2. Now again, you might need the approximate y values for these, which you can just get from a calculator. All right, so now let's put the graph together real quick. Okay, so let's pretend the graph isn't on here. And so let's say I plot the extreme values, -1, 2, and then I plot 1, -2 for that. And then I plot the intercepts, which would be here and here, and then I plot an intercept here. And then the other thing I've got to plot is I've got to plot the points of inflection. Well, the points of inflection occurs at about -0.7, and you can get the y value by just plugging -0.7 into the function. And so there's points of inflection there, point of inflection there, and a point of inflection there. And then we can determine, where the function is increasing, where it's concave up, where it's concave down, and so forth. And then we can plot the graph through these points. So we know along this route it's increasing and concave down, and then here it begins decreasing, concave down. Then here it switches to concave up, still decreasing. Then it's still decreasing, but it switches to concave down. And then here it's decreasing, concave up, and then it goes through here, increasing, concave up. And I'll do some more examples on the next video, but that's pretty much how you curve sketch using calculus.